So, in the first week we introduced little bit of quantum mechanics, totally different formulation of physical world, and we found that hydrogen atom has played a nice role, and Niels Bohr's postulates or assumptions or his model was a great step towards this quantum mechanics. And very special ideas were introduced in that, and that helped in understanding the spectrum of hydrogen atom. The most important thing is that there are certain specific states of this particle, of this atom, described in terms of circular orbits, in which the atom was allowed to deviate from the classical electrodynamics, classical physics, that acceleration of charged particle must be accompanied by radiation. So, this was a major difference. And then how to get those stationary orbits, how to get those fixed radii, specific radii, so that in only those circular orbits the electron can stay without emitting radiation. So, for that some Niels Bohr did some things which was equivalent to finally the quantization of angular momentum, that the angular momentum of the electron about the nucleus should be integral multiple of h cross. So, here the quantum mechanics is introduced. Angular momentum can take either the value h by 2 pi or 2 times of that or 3 times of that, only then you get those specific radii. After that it is all classical physics. After that it is all, you have a nucleus here, positive charge here, and electron going in circle. So, you say that potential energy is given by that Z e square. So, if it is a single proton, then it is E square over 4 pi epsilon naught r, and the kinetic energy is half mv square, and then F is equal to ma, mass into acceleration, and acceleration is v square by r. These are all classical equations we are used to. But together with this, when this is introduced, the Planck's constant enters, and the quantization n can only take integral values, that enters, it gives you the essence of quantum mechanics. So, there are only certain radii which are possible, which will follow this, that are stationary orbits, and electron can go in those orbits without radiating anything for quite some time. But then the jumps are allowed. If you have an orbit here, if you have an orbit here, the electron is here, and if this electron can make a jump here, right, and then it can emit energy. Okay. So, using these things we derived the expressions for energy, and the energy for that nth orbit was me4 divided by, with a minus sign here, 2 times 4 pi epsilon naught square, and then h cross square, and 1 over n square. And this whole thing, which is a constant, that turns out to be almost minus 13.6 eV, and therefore this divided by n square. So, if angular momentum is quantized, energy is also quantized. So, n equal to 1, you have energy minus 13.6 eV. So, n is equal to 1, you have energy minus 13.6 eV. N is equal to 2, it will be divided by 4, so 3.4 eV. So, n is equal to 2 is minus 3.4 eV. N equal to 3 will be this divided by 9, so it is something like 1.5 eV. These numbers which I am giving are not very accurate up to 3, 4, 5 significant digits. I am giving you the broad values, but this is the right expression, and you put the values and get the exact energies from here. Similarly, if you go for n equal to 4, you will have this divided by 16, so it will be minus 0.85 eV, I believe. Like that you can go beyond. So this was to get that energy levels, allowed energy levels. This hydrogen atom can have this energy or this energy or this energy or this energy, depending on which circular orbit this electron is going. And then the next part was the radiation. This is the allowed energy values, but electron will be in one of these allowed orbits only, and usually it will be in the lowest energy state, which we call ground state. So it will be in n is equal to 1, having energy minus 13.6 eV, and therefore not radiating anything. Hydrogen atom in a gas jar, where all the atoms are in ground state, or almost all the atoms are in ground state, will not radiate anything. Okay, but by passing that discharge or giving energy, somehow electrons can be made to go to higher orbits, and if they go to higher orbit, then they can make jump to the lower orbits, and in one jump a specific amount of energy is released. So if the jump is from, say, n is equal to 3 orbit to n equal to 2 orbit, if this is the jump, if you have this n is equal to 3 somewhere, and then this is n is equal to 3 and this is n equal to 2, and it makes a jump here, the electron makes a jump here. So the energy is reduced from minus 1.5 eV to minus 3.4 eV. So the energy is reduced, and that difference is it was in n is equal to 3, so minus 1.5 eV, and now it has gone to minus 3.4 eV, and therefore this is 1.9 eV. This much energy is to be released in the form of radiation, and then we have another wonderful quantum idea that this light is waves as well as particles. So when I talk of energy, a specific amount of energy, in one jump it emits one lump, and that one lump has this much of energy. So I can count, these are called photons, so I can count the photons. So it's a particle character. But once it is emitted, once it is in our spectrometer and we are doing experiments, it's showing its colors, it's showing its wavelengths, it's showing its frequency. So that wavelength, frequency, which are wave characteristics, and then energy and linear momentum, which are particle characteristics, both are interrelated. A same object, same entity, which we call radiation or light, has photons. You can describe it as photons which are countable, 1 photon, 2 photon, 10,000 photon, 10 to the power 7 photons, and so on. Each photon having a definite energy, each photon having a definite momentum. Or you can talk in terms of waves. It is waves, and you have a wavelength, you have a periodic variation of electric field and magnetic field in space, and that periodicity in space is wavelength, and periodicity in time is frequency. So the same object can be described in terms of particle parameters, in terms of wave parameters, and these are interrelated to each other. That is another wonderful quantum idea. And the relations are, the wavelength will be given as Planck's constant into speed of light in free space or vacuum divided by the energy. Alright, so this is the kind of relation between energy and wavelength, and then momentum also you can talk. The momentum will be P equal to h by lambda, or lambda is h by p. So these are the relations. So you can work out the wavelength for this transition, n equal to 3 to n equal to 2. You can work out how much is the wavelength. If this is the energy, what is the wavelength? Put this energy here and you get wavelength. So for 1.9 eV of energy lump, that photon, the corresponding wavelength lambda will be hc divided by 1.9 eV, and h into c, Planck's constant into speed of light. If you put the values and then convert in the units which I am going to use, this is very close to something like 1240 eV nm. Okay, what is that? eV is for energy, electron volt, you know that, we have used it. Nm is nanometers. So eV nanometer, in this unit if you write Planck's constant into speed of light, that will be almost this much divided by 1.9 eV. And that turns out to be close to that 656.3 nanometer, which is the measured value of one of those 4 wavelengths which are emitted by hydrogen atoms. So to explain that wavelength which is emitted by hydrogen atoms, so much of hard work had to be done. Then one could come out with a kind of a model or a theory that okay, this is what happens inside this hydrogen, and that is how this is emitted. You can go ahead. This is n equal to 3 to n equal to 2. If you have n equal to 4 to n equal to this transition, n equal to 4 to n equal to 2. So n is equal to 1, you remember this is minus 13.6 eV, this was minus 3.4 eV, this divided by 4, and this was minus 1.5 eV, and this is minus 0.8 eV, and so on. So you can work out if it goes from n equal to 4 to n equal to 2, how much will be the wavelength. That matches exactly with that second wavelength which is emitted. Okay, remember that these wavelengths are, this is 1 and the other wavelength, next wavelength is 486.1 nm. Then you have 434.1 nm, and then you have 410.2 nm. So just work out, this was n equal to 3 to 2, this corresponds to n is equal to 4 to 2, and this one is n is equal to 5 to 2, and this one is n is equal to 6 to 2. So transitions ending at n equal to 2, originating from n equal to 3, 4, 5, 6 gives you all those 4 wavelengths which were experimentally seen long ago. So that is how it works. So it's very successful in terms of explaining these wavelengths, and it introduced so many of quantum ideas. Okay. But then with so much credit, so much of respect given to Niels Bohr's model theory, there are serious limitations, and that is how science goes. You put a major step and you devise something very new and some new theory and all that. But then when the technology advances, when the experiments become more sensitive, then the need of, or some new observations come in, then the need of modifying that theory, coming out with something else is always That's the kind of scientific evolutions. So this Niels Bohr's model in terms of circular orbits, which tells you that if U of r, potential energy, is minus E square over 4 pi epsilon naught r, then it turns out to be all those energy levels. Energies are given by that expression that I wrote, minus me4 and then 2 times 4 pi epsilon naught square h cross square and n square. So this works quite well. And not only that, if you have one electron and more than one protons in the nucleus, which we call hydrogen like ions. For example, if you have helium nucleus, so helium nucleus has 2 protons and 1 or 2 neutrons, so 2 protons here and 2 electrons here in the atom. So if one electron is knocked out, you have helium plus. So what is the structure? You have 2 protons pp and of course neutrons, and then you have 1 electron left. This is your He plus. Of 2 electrons, 1 electron is knocked out, and then you have this He plus ion. For this, the potential energy will be given by 2 times of this. So let me write Z times of this. If there are Z protons in the nucleus and only 1 electron, then you have ion, where the potential energy will be given by this, and then this En is modified by multiply this by Z square, and everything works quite well. The radius will be divided by, the radius will be A naught divided by Z. So everything works quite well. Okay, let me write the first one only, the first one only. Others also go by the same way. So this is how it works quite well. You can have lithium double plus, you can have lithium double plus. So lithium has 3 protons and neutrons and then 3 electrons. 2 of them if you take out, you get this lithium double plus. For this ion also you get energies and radii, all those things, using this circular orbits and Newton's law. Circular orbits and Newton's law, m times v square by is the force which is towards the center, and all those things you can work together with the quantization L equal to NH cross, and you get the right things. But then if you talk of helium atoms, not helium ions, helium atoms, where you have 2 electrons, you have 2 protons and then you have 2 electrons. That means the potential energy of any of these 2 electrons, if you write in the field of the nucleus and the other electron, it is not of Coulombic type. It is not of 1 by r type. So if the potential is different from that 1 by r type, it turns out that this model in terms of circular orbits, or if you stretch it to elliptical orbits and all those using classical physics with quantization of course, it doesn't work well. The spectral lines, the radiation which is emitted by helium atoms when you have helium discharge tube, those wavelengths are not obtained nicely using these circular orbits. So there are problems even for hydrogen atom, even for these wavelengths which are there, if you go with a much sensitive instrument, which now we can do, we find that there are deviations. This line 656.3 nanometer is not one line. Very close to this wavelength you have splitting, you have several wavelengths very close to this. The difference is something like 0.01 nanometers, but there are discrete more than one lines there, and that is not understood by those circular orbits. So once the potential is different, then this Bohr's model cannot be extended much beyond this hydrogen like ions. So something new has to be brought in, something new has to be brought in. We have to have a formulation of quantum mechanics where we can work with many more kinds of potentials and get those energy levels and all those things. And those first 2 decades of 20th century were very, very productive, where great minds worked on it, and now we have several workable theories or models or procedures to get these things. The one which we will be using, or I will be describing, is that Schrodinger's formulation of quantum mechanics, where in a particular way those energies and all those things are dealt with. So let me talk a little bit of that Schrodinger's equations and Schrodinger's method of getting those energies. So the central equation is minus h cross square by 2m. H cross is that same Planck's constant divided by 2 pi, and then this del square, I'll just talk about it, and then you have a function of space point xyz. You can write this as a function of xyz or whatever coordinates you use to describe a point in the space, and then v, this is, or u, potential energy. Let me write v. People write v generally. V of the same position, and then the psi of r, that is equal to E, this is energy, and then psi of r. This equation is known as time independent Schrodinger equation. So that means there must be a time dependent Schrodinger equation also, and it is, but I won't be talking about that. So this is known as time independent Schrodinger equation, and here is that potential energy. Here is that potential energy. Potential energy function. Like in the Coulomb hydrogen atom case, this was E square over 4 pi epsilon naught r. R you can write as square root of x square plus y square plus z square if you are using Cartesian coordinates, or r if you are using spherical coordinates. So this is that potential energy function, and this is that total energy we are looking for. And where is that quantization n? N is equal to 1, 2, 3. How it will be quantized? It will be quantized by this equation itself. So first let me tell what is this del square. So del square, if I am using Cartesian coordinates, it is written for partial differentiation d2 del 2 del x square plus del 2 del y square plus del 2 del z square. And if you put psi in front of it, del square of psi, that means this. And what does this mean? This psi, we call it psi, right? Greek letter. This psi is a function of space point. That means I have some origin somewhere, and this is that position r. So different points in a space have different position vectors, and it is this position vector that I have written here. So I can write this in terms of x, y, z also, or r theta phi, or any other coordinates I use. Give me x, y, z, I know which point you are talking, or give me the point, I will know what x, y, z are. So these are functions of x, y, z. This psi is a function of x, y, z if I am using Cartesian coordinates. And then if it is a function of x, y, z coordinate, this expression means that you differentiate with respect to x and treat y and z as constants for this differentiation. Similarly, for this differentiation, differentiate with respect to y twice and treat x and z as constants for this differentiation, and similarly here they are known as partial differentiations. So that is the meaning of this function, and this is simple multiplication of potential energy function and the psi, and then you have this energy and this psi here. Then there are certain conditions on this psi function. Right, the psi function is very mysterious function, and this is known as wave function. Okay, this is known as wave function, and it's a function of position vector or the position of the point. I am still in a very preliminary section of quantum mechanics. So there are other parameters other than the position vectors which can enter into the psi, but I am just not talking of that. Spin is one, spin angular momentum or spin magnetic moment is one that can also contribute to potential energy. So those things apart, simpler situations. So this is a function of position vector psi are known as wave function. And the state, now this is a very crucial statement, state of the particle at an instant, right? In classical physics, when I say state, what is the state of this chalk? You will say, okay, it is positioned here and its velocity is 0 or like that. So state means give me all the information about that particle. The particle is in this state, right? So similarly here, the state of the particle, that means whatever information is available, that information I need to have. So the theorem is, or the central idea is, that this wave function, which is a function of space point, which is a function of x, y, z, that function is the description of the state of the particle. State of the particle at an instant is described by this wave function, by its wave function at that instant. The wave function can change as the time passes, and how it will change, for that you have another equation which is known as time dependent Schrodinger equation. Okay, and so that means, in classically, if I ask what is the state of this particle, where the particle is, you will give me some numbers. The particle is here, it has this velocity or this momentum or this magnetic moment or this and that, you will give me some numbers. But in quantum mechanics, if I ask, tell me the state of the particle, give me the informations about the particle, you will give me a whole function, a whole three-dimensional function, which has different values at different positions here and there and there and there, and that whole function will describe the state. So it's a very abstract kind of thing, and how it is related to the actual parameters which I measure in experiments. What I measure? I will measure energy, that will be in numbers, the minus 13.6 electron volts. I will be measuring position, I will be measuring momentum. So whatever quantities I measure in our experiments, they will be in numbers. And how those numbers are related to this wave function, that is a different procedure. But if this potential energy function is given to me, then this psi is something which I have to discover from this equation. I have to find this from this equation. So it's a kind of unknown function, not unknown variable. It's an unknown function, and this energy is not known to me. This is an unknown function, unknown value. This has a value. This energy is a value. It is just a number. It's not function of x, y, z, etc. It's a number. So this E and this psi, I have to find E and psi so that this equation is satisfied, and there are certain restrictions on this wave function. For example, this wave function should go to 0 if I go to very large distances from the potential centers, or if I do some kind of a squaring and integrating, it should not blow up, it should not go to infinity, it should not be discontinuous function, it has to be continuous functions. So there are some restrictions. So within those restrictions, try to find this energy E and this psi which can satisfy this equation, and you will get quantized only specific values of E and specific functions psi, each corresponding to one energy value. So that is how this quantum mechanics of described by Schrodinger equation works. We will talk more about this wave function and this Schrodinger equations in the next lecture.